So we have developed several ideas of quantum physics, quantum mechanics, and the description that we are using is Schrodinger's description or Schrodinger's formulation of quantum mechanics. There are other formulations also. In this, the central equation is in terms of a function which we call wave function, and that equation, once again let me write, minus h cross square over 2m del square, remember del square, psi of space coordinates, then plus potential energy function that is also dependent on space coordinates in general, and then this psi r once again multiplication by this, that is equal to E psi. So essentially in this equation we have this E which we want to find, and then we have the psi that we want to find. This psi r, which is known as wave function, it's supposed to contain all the information about that particle which is subjected to this potential, and everything about it is contained in this wave function. If it is solution of this equation, which is known as time independent Schrodinger equation, okay, time independent Schrodinger equation, then this corresponds to a stationary state in which the energy is definite. When I say definite, that also has a big physics in it, but let me suppress it for the time being. So with a definite energy, if the particle is existing in this potential, then this equation gives me this wave function, and this wave function that contains all the information. Now for hydrogen atom, where u of r is, it only depends on the distance from the origin, from that nucleus, from the proton, and that is minus e square over 4 pi epsilon naught r. So for hydrogen atom, if you solve this equation, and remember you have to follow the boundary conditions, that this psi, this wave function has to be finite everywhere, all those boundary conditions. Then it should go to 0 at infinite distance from the origin, it has to be continuous, all those conditions are there, and then it has to be square integrable. So keeping in mind that the psi has to satisfy these boundary conditions and this equation, you have to find E energy as well as this function psi which satisfy this equation and this. And if we look for those functions, it turns out that there are some specific wave functions, and those wave functions with and there's naturally some specific energies. Okay, so the energies turned out to be the same as that in our Bohr's model, which was minus me4, then 2 times 4 pi epsilon naught square h cross square n square, the same. So for n is equal to 1, that means the lowest one, the energy is minus 13.6 eV. Next one will be minus 3 eV and so on. So for this energy you can find psi r. Okay, if you take some other energy, say minus 10 eV, maybe you will not find any psi there. So for this ground state, we have our a particular wave function, and that wave function has a value. Then you have n is equal to 2, which corresponds to E equal to minus 3.4 eV. Now interestingly, that we discussed last time, that a wave function is described in terms of 4 parameters n, l and ml. This equation will give me a function which can be characterized by these 3 numbers, these 3 parameters n, l and ml, in which n, which is known as principal quantum number, can take values 1, 2, 3 integer values. This L, which is related to angular momentum, this can take values 0, 1, 2 up to n minus 1, and then this ml, which can take values from minus L to plus L in steps of 1. So those things we discussed. So that means if you tell me what is n, what is L, what is ml, I know that there is a function, you are talking of a function, and the function is in terms of space coordinate, and spherical coordinates will be best suited. So you can get a function in terms of r, theta and phi. R is the distance from the origin, and theta and phi are angles which describe the orientation. So the wave function is completely fixed in terms of these quantities. But then you also have spin angular momentum, for which I cannot describe any picture, because this is something which is beyond all classical descriptions. So nothing like electron is spinning about its diameter, there is no diameter of electron, so nothing of that sort. Any kind of motion in the space, the angular momentum corresponding to that is orbital angular momentum, and that is already there in this L and ml. So that spin part is purely quantum phenomena, there is no analog in classical mechanics for that, but it does exist, and for that we write our function as we just write a function for which I don't give any functional form, okay. But then it is chi ms, and that ms can take 2 values, minus half or plus half. Then we talked of magnitude of angular momentum. The magnitude of angular momentum is L plus 1 square root of that h cross, that is the magnitude of orbital angular momentum, and here it is square root of s plus 1 and then h cross with s equal to half. So for all electrons s is equal to half. Here this L can take value 0, 1, 2 etc. So different electrons can have different L, but all electrons have the same s, and here also it goes from minus s to plus s in steps of 1. So all those things we discussed. So if I give you all these parameters, all these quantum numbers, 4 quantum numbers for hydrogen atom, I have given you a quantum state, okay, a quantum state. A quantum state means the entire information about the system which it is possible to have is contained in that, and from that quantum state, how to derive those information, that is a separate chapter. If I know the wave function, let me write one wave function once again for n equal to 1 and n equal to 2 also. So for n is equal to 1, that means energy minus 13.6 eV, the wave function is L is 0, only one value of L is allowed and only one value of ml is allowed. So the wave function is written as 1, 0, 0. The first one is n, the second one is L, and the third one is ml, and that turns out to be 1 over square root of pi a naught cube and then e power minus r by a naught. A naught is the Bohr's radius. So this is the wave function. And then barring spin part, how this contains all the information about the electron. First, let us see the probability density of finding the electron in some detour, some volume. So, if you have a volume here, if you have a small volume here, detour, and this is at position vector r, then the probability is P at that in that detour. So, that is the probability P at probability in that detour there. So, this you can write that as, let us write dP. That probability is this thing, and if you can do that, this is 1 over pi a naught cube and e power minus 2r by a naught, right. And then where the electron is, to be found, to be located. So, this function has that information, this function, and from this we have derived this. So, this gives me that probability. Now, if I ask in terms of the distance from the proton, that means I take a distance r and I draw a spherical surface. All points at distance r will be on this surface, and then I take another surface with radius r plus dr. Okay, another surface with radius r plus dr. Then I have a spherical shell. Inner radius is r, outer radius is r plus dr. So, if the electron is anywhere in this shell, the distance from the proton is between r and r plus dr. What is the probability of that? So, I ask for probability of finding the electron at a distance between r and r plus dr from the nucleus. So, if I ask for this probability, and that probability, that is psi r square dτ, in fact you have to multiply by dτ, then you get the probability. So, this is mod psi square, which is this much, which is 1 over pi a naught cube e power minus 2r by a naught. This is this part, and for dτ you will be writing 4 pi r square dr. The volume that I am allowing, that volume is that of that spherical shell, and that volume is 4 pi r square dr. So, the probability that the electron is at a distance between r and r plus dr is given by this function. So, it is this pi can be cancelled. So, 4 divided by a naught cube is 4 divided by a naught cube, and then r square and e to the power minus 2r over a naught, and then dr. So, this thing is known as radial probability density. This is known as radial probability density. Okay. So, it gives you this dr I am leaving out. So, it is a probability density, radial probability density, you multiply by dr and you get the probability in that dr width that I have given, r to r plus dr. So, this is radial probability density, and if you plot this radial probability density as a function of r, radial probability density, let me write PR here as a function of r. So that turns out to be something of this, like this type. And the maximum turns out at a very nice separation, at a very nice distance from the origin, and that nice distance is nothing but Bohr's radius A0. So in Bohr model, in ground state, in the lowest energy state minus 13.6 eV, the electron was allowed only one distance from the proton, and that was A0. That was Bohr radius. That was 0.053 nanometers. So that's it. But here there is a probability of electron at this distance, much smaller than A0, close to A0, at A0, more than A0, like this. So in this Schrodinger picture, the electron is not going on a circle, not confined at the surface of a sphere. Its distance from the origin, from the proton, is not definite. Its distance from the proton can be anything from 0 to infinity, in fact. Of course, the maximum radial density turns out to be at A0. The maximum probability density, radial probability density, is at 0.053 nanometer, but all these ranges are probable. You can have electron here, you can have electron there. And since this wave function does not have any theta dependence, it doesn't have any theta dependence, therefore this probability density is also symmetric, spherically symmetric. So if you want to make a picture, mental picture, in Bohr's model we had the mental picture that is going in a circular orbit. But here if you want to make such a mental picture, you have to make some kind of a cloud with varying density. At Bohr radius, its radial density is more, and otherwise you have density less, then density more, and then again density less, and so on. So it's a cloud, it's a big cloud, it's extended cloud. It can extend to anything in principle. Of course, this at what length it becomes insignificant. Okay, so that is given by this scale. How many times of A0? A0 is 0.053. So 10 times of that, 15 times of that, 20 times of that, like that. It's insignificant. So it doesn't mean that at 1 meter you will find the electron. It will be still in nanometers only, but then not at A0 alone. So that's the kind of picture for this. So this is about the location, this is about the position. If I go and locate where the electron is, these are the places where I can locate, and these are the probability of those places, finding the electrons at those places. But then it has other information in it. It says that L is equal to 0. This wave function corresponds to L is equal to 0. So it tells me that the angular momentum, orbital angular momentum, is 0. Once again, see the deviation from Niels Bohr's model. In Bohr model, the ground state n is equal to 1. We had the quantization rule. Remember that quantization rule? In Bohr's model, the quantum physics was introduced into classical description using this L is equal to NH cross. So for n equal to 1, L is H cross. That is how the equations started, and we got those energy expressions. So in ground state, in Bohr's model, the angular momentum is h cross, but the quantum description, Schrodinger's description, when we are doing L is equal to 0, angular momentum is 0. And then z component of angular momentum is also 0. So angular momentum is known from this wave function. Other quantities can also be obtained from this. Anything, linear momentum, kinetic energy, potential energy, anything, you have information contained in this. It may be definite, it may not be definite. The energy is definite, the angular momentum is definite, but the position is not definite. You can have all positions are probable. So similarly, if you go for, let's say, kinetic energy, maybe kinetic energy doesn't have a definite value at a given instant. There are probabilities of different kinetic energies. But that probability is, how much is that probability? That can be obtained from this wave function. So that is why I say, once I have the wave function, I know everything that it is possible to know about that system. So if you completely specify a function, in this case the spin part has to be included, plus half or minus half. So that becomes a quantum state. The particle is in that particular state. And in our case, that state is defined by those 4 parameters n, l, ml and ms for hydrogen atom. Now let me talk of the first excited state, that is n is equal to 2. So if n is equal to 2, the energy is minus 3.4 electron volt. Now L can have two values now, 0 or 1. If L is equal to 0, with L is equal to 0, ML has to be 0. And then my wave function is 2, 0, 0. This is how I will write it. The wave function is psi 2, 0, 0. So you have N here, you have L here, and you have ML here. It can also be L is equal to 1. If L is equal to 1, then ML can be minus 1, 0 or plus 1. It can go from minus L to plus L in steps of 1. And then we will have psi 2, 1 minus 1, psi 2, 1, 0 and psi 2, 1, 1. So we have 4 functions, 4 different functions. These are different from each other, independent of each other. I have 4 different wave functions possible with the same energy, minus 3.4 eV. Okay. So what I will say is that here for n is equal to 1, let me write it here. For n is equal to 1, we had only one wave function psi 100 with that energy, minus 13.6 eV, and on top of that I had this psi chi ms. Ms can be plus half and minus half. So I had 2 different quantum states. I had 2 different quantum states, and these 2 different quantum states were differing only in spin part, not in space part. Space part was identical, which was given by that wave function. But if n is equal to 2 and I am going to first excited state, there are 4 different, 1, 2, 3, 4 different wave functions. And what is the difference? Yes, the difference is in the space part. Here the angular momentum is 0. Here the angular momentum is 1. L is equal to 1. So the magnitude will be root over LL plus 1 times h cross. So those things are there. So here for these 3, L is equal to 1. For this one, L is equal to 0. And that reflects in that theta phi part. The wave function will have theta phi part. This is spherically symmetric, L is equal to 0, but for L is equal to 1, you will have theta phi part. And that theta phi part will be different in these three, because ML is different. ML is minus 1 here, ML is 0 here, ML is plus 1 here. So I have 4 different kinds of wave functions, and with each of them you can put the spin part, and that spin part is once again chi ms plus half and minus half. So how many states are there? How many quantum states are there with this energy? 4 different wave functions, 1, 2, 3, 4. With each you can put chi plus half or chi minus half. So there are 8 quantum states. You have 8 quantum states. Likewise things will happen. Now let me also tell you a special kind of nomenclature that people use. This L is equal to 0 is called S. L is equal to 0 is called S. L equal to 1 is called P. L is equal to 2 is called D. L is equal to 3 is called F. S, P, D, F. So if I have this state here, this state here, N is equal to 2 and L is equal to 0. So this will be called 2s state. This will be called 2s. And when you specify N and L, okay, when you specify N and L, then you call it orbital. So 2s is an orbital where N is equal to 2 and L is equal to 0, and ML is anyway 0, but that is not mentioned here. Okay, so 2s. So 2s will have 2 quantum states, because your wave function is fixed 2, 0, 0, but then you have 2 spin states, so there are 2 quantum states in 2s. How many quantum states are there in 1s? Once again, N is equal to 1, doesn't matter, L is equal to 0, S state, 1s, L is equal to 0. If L is 0, ML is 0. So only one wave function, and then chi ms equal to plus half minus half, once again 2. All S states will have 2 quantum states. Similarly, all P states, these are P states. Here L is equal to 1, so it is P, this is 2P, all these are 2P states, all these are 2P, orbitals rather. These are 2P orbitals, okay, and in 2P orbital, you can have this or this or this, so 3 wave functions, space part of the whole thing. This is the space part, depends on r, theta and phi, so 3 and then a spin part, so into 2, that is 6. So 2P will have 6 quantum states. All P, 3P, 4P, every P orbital will have 6 quantum states, right? So you can count the number of quantum states in an orbital, or if only principal quantum number is given, n equal to n, 1, how many quantum states are there, n equal to 2, how many quantum states are there. So those things can be counted in this fashion, remembering that L goes from 0 to n minus 1 in steps of 1. You can count, and then ML, for each L, ML goes from minus L to plus L. You can count. So this way you can count the things. So we have done enough with hydrogen atom. Lots of quantum ideas have been introduced. It will take time to digest them because they are very new kind of things for which we don't have any intuition from our daily life. But as time passes, you live with quantum physics, you will feel comfortable. Okay. So, from next lectures we will be doing quantum mechanics of larger atoms and finally solids, and then we will talk of conduction.